Good evening, class. The last time we met, we covered hydrology and flood routing. This week, we will be looking at two topics, level pool routing and channel routing, where we will cover the Muskingum method. Okay, so for the past few weeks, we have been looking at level pool routing examples. We've been using words like inflow, outflow, and storage, but what exactly do these represent? So, behind me is this diagram here that represents the outflow, the inflow, and the region between it, when you subtract the inflow and the outflow, is the storage. Okay, so now that we've placed a definition on it, let's go a little bit more in depth. The inflow refers to water entering the system. The outflow refers to water that is either being detained or water that is just being drained out. The storage is the in-between between the inflow and the outflow. Okay. Defining keywords is an extremely important part of the learning process. It helps us to understand the topic at hand. Now that we've filled this gap in, let's see how these variables are related. These variables are related using the continuity equation, which is as follows. This is the continuity equation, and at the top here, this is the equation we're going to be using in order to solve problems with the level pool routing method. The storage and the outflow are usually the unknown parameters. We usually look for these two, and they're related through the function 2s over del t, 2s over del t plus q. Okay, so now I want to take you through the general procedure to solving problems using level pool routing. The first step is you identify what is missing. Sometimes when you graph out, or you not graph out, if you separate what you have and what you do not have, it usually points to the method you use to solve the problem. Okay, it also tells you what you're looking for. The second thing that we would do is we would look to see if we have any weirs. If we have weirs, then we have a weir coefficient. So we'll need to be very careful about these coefficients and some other orifice factor, k. The k is the weir coefficient, or it can be anything else depending on the situation. The next thing that we do, and I'm assuming that we have a weir, the method would certainly change, is you find the flow. The flow is found using k, l, h, and n. So what you would notice off the bat from looking at this equation is that the flow is directly related to the length and the height of the weir. So that's just something to be conscious of when working with these problems, that your length and your height definitely impact the flow. Okay, now if we take a look at this level pool equation, how exactly do we delve into this? What you would do is you would compute your volume. Okay, the volume is your plan area times the height. Okay, now once you have the plan area times the height, you add it to your outflow in order to get this portion of the equation. See, there we go. Usually we use software like Excel in order to determine these. And now that we've spoken about this equation, we've already mentioned the length and the height of the weir. This would impact your storage. So now what we would do is we would plot the outflow, and we also plot this portion. The height interval is something that we assume. The column for height is usually assumed by taking a reasonable guess, comparing how long is our section and what intervals can be chopped up into. Okay. Now that the general columns are complete, you would set up linear interpolation in order to move through your channel. Okay, the next thing that we do is we compute 2s over del t minus the outflow, which is the segment here. The segment here, just as we did this one, it's computed in the very same way, except you need to be very careful with the time intervals. This is a step further, and this is one step back. Okay. So the next thing that you would do once you satisfy each term is you would graph it out. In order to correctly do this, because we're working with so many variables, we use Excel and we separate each of these quantities. We tabulate it. We tabulate it as follows. We will have our 2s over del t plus q in one segment. We'd have this in another segment and this too. What we would do once we have found all these parameters is we will graph it. We will graph the 2s over del t plus q and the outflow, and we would find our peak. Now, how you would know that you are on the right track is when you graph it out using whatever graphing tool you're working with. If supposing you graph it out, this is 2s over del t plus q, and then what's the outflow, and this is, if you come here and you come here, you must always have the falling limb. The two graphs must intersect on the falling limb. This would be your inflow and this would be your outflow. This value must always be bigger than that. So again, let's repeat that. If the intersection of the graph is on the falling limb and the inflow is greater than the outflow, then you know that you are on the right track. The important question that we haven't asked yet is, why is this important? In level 4 routing, why do we need to understand it? Why do we need to be careful? And why do we need to determine these values? So the reason for this is because supposing you are the engineer tasked with the job of designing the reservoir or managing the stormwater situation. What would happen if you designed it incorrectly or you did not accommodate the accurate storage? Firstly, it could lead to infrastructure damage, and as a developing country, we certainly cannot afford that. Water damage is very serious, especially in pavements. So what could happen is it could potentially flood the area, and that could damage the infrastructure, crack it. It could separate people from other segments of the city. Okay, so now we're going to take a look at channel routing and the two types of storage we need to be familiar with. So first of all, there's prism storage, and secondly, there's wedge storage. So prism storage operates under the idea that there's only uniform flow occurring. Right, so by definition, a prism means that the top face and the bottom face are equal. Right, so this idea is that there is uniform flow. Uniform flow is the only kind of flow that persists. But of course, we know that's an idealized situation. In real life, more often than not, that does not happen, and we have what we call wedge storage. Wedge storage is when the velocity changes per unit time, and that's what we call unsteady flow. It's a non-idealized situation, and it's one that we encounter a lot in the real world. Okay, yeah, that's about it. Okay, so now we're going to take a look at channel routing, specifically the Maskingham method. So the Maskingham method is where the storage is expressed as a function of the inflow and the outflow, and it's governed by the sets of equations listed on the board. Okay, so what is done for the Maskingham method is the time intervals between each step is considered. Eventually, we will need to find the k value and the x value, which are time intervals and the storage respectively. Okay, so what we will need to determine if we are subjected to a problem through the Maskingham method is we'll need to determine the numerator and the denominator. The cumulative values will also need to be determined as well. So once we have the cumulative values, what we would do is we would graph out n and d, and we would adjust the x value. The x value is something that's usually played around with. So what you would do, especially on software like Excel, is you would vary the x value. So what you would be trying to accomplish is, supposing your curve initially looked like this. When you vary the x, let's say for example x was 2, just a random example, then perhaps your graph went something like that. If you said x was 1, perhaps your graph got a little bit closer, but not quite. So the point of this is to find some kind of sweet spot where the graph becomes well aligned. And that's the essence of the Maskingham method. These parameters here are weighting parameters, and once these are computed, you use it to find your peak outflow. Okay, so what you do is you would graph out your inflow and outflow, and you would try to establish the peak. Okay, it now tells you whether you have flood attenuation or not.